Good morning or good afternoon. I'm Jean-Louis Van Bellen. I'm gonna do a small video for a special friend of mine. It's Valentine's Day, and so it's a friend who likes to talk a lot about, alien life and the possibility of making contact with them and possibility of them visiting us. The secondary topic of the talk is a bit the idea of the end of science. Did we discover all of the laws of nature? And is all that is left engineering then? Maybe, maybe not. I'm gonna try to structure the talk a bit better than I usually do. I have very few slides, only 4, and it's gonna take quite a while to go over them. But I'll follow a text that I've uploaded on my ResearchGate site. So the topics are a bit forces and distance scales. It's very important that we sort of have a basic idea when you talk about, cosmology and, the beginning of time and all that, we sort of know what forces are and what different forces there are and how they are related to, a very, very different distance scale, the micro and the macro. Then, gravity, of course, that's sort of what rules the universe. All galaxies then rotate around, galaxy that expands, the universe that expands. Then I'm going to talk about the closed universe, mention some numbers there, some ideas, the mass of the universe, and then the beginnings. How did it all start? How should we imagine that? And then the idea of, the idea is basically there was a Big Bang, and then, the universe expands, and maybe it will contract again. Could it be oscillating? How should we imagine that? And then the main topic, indeed, life on Earth and life in other places, perhaps. Could we communicate with them? Is there a chance that there is actually, a lot of life outside that we can that we could possibly get in touch with? So I start with some really basic equations, indeed, as I said, sort of the force laws. The basic equations of the universe, I'd say, is the Planck-Einstein relation. So that's the energy is proportional to Planck's quantum of action, h, and we multiply it by a frequency, and that gives us the energy of elementary particles. And then we have the second equation, Einstein's mass-energy equivalence relation, E is mc squared. We can add both, and then we have sort of one of these equations which is difficult to read, but has a lot of meaning. On the one hand side, we have, on the left hand side, we have mass divided by frequency. Those are two measurable, observable properties, characteristics of particles or of systems. And on the right hand side, we have h divided by c squared, which are two absolute constants of nature. So that's basically the idea that our description of the universe is always expressed in these equations, and in these equations we have parameters, nature's constants, and then we have the observables, the measurables. Those measurements are relative; they depend on our frame of reference, but it doesn't mean that that isn't real. Elementary particles are real; their energy and mass is real. We just measure it differently according to our frame of reference. We have space and time, of course, as we always think of things happening in space and in time. These are what Kant called a priori categories, categories of our mind. They are very different. The philosophical question of, can we go back in time and whatever, I settled that in previous lectures. I have those two graphs there. Basically, both the idea of space and time are related through the idea of motion. A particle or a system moves in time and in space, and that motion needs to be a regular function. On the right hand side, you have that spaghetti thing, which basically implies that an object could be at two places at the same time, which clearly nonsense. So on the right-hand side, that green curve, we have a very wild oscillation, a particle that goes back to where it was, with accelerations, decelerations, very wild. But it's possible. It's theoretically possible. It's a regular equation of motion that we are graphing there, and so yeah, time goes in one direction only because of logic. So on the right-hand side, Kepler's law for orbital energy of orbitals. We can always write sort of the energy of an orbital as being equal, or the energy divided per mass unit, as v squared divided by 2 minus mu. Mu is a standard parameter. It depends on the force. We can have the gravitational force, the electromagnetic force, Coulomb force, or the nuclear force. And so that's the two equations below it, where basically we model nuclear and electromagnetic oscillations. En, the N stands for nuclear, and EC, the C stands for the Coulomb. So these are the energy equations for, well, it's a general orbital energy equation, and we have nuclear and electromagnetic energy equation. So we would be talking about scales. The difference between a nuclear and electromagnetic oscillation is that standard parameter that we use, nuclear parameter, mu n versus mu c. And if we take the ratio of that, we find it's 1, which is kind of normal, because in the nuclear oscillation, we have a range parameter. The nuclear force become much stronger than the Coulomb force at very close distances. And so we're going to model that by a range parameter. And we define that range parameter basically as the distance for which the two forces are equal. The two forces are equal but opposite. And so would say sort of the distance at which these forces work are basically the same order of magnitude, but the nature of these two forces is very different, of course. We think of a nuclear oscillation as an oscillation in 3 dimensions with two axes of two oscillators that are perpendicular to one another, and an electromagnetic oscillation is basically an oscillation in a plane. We also have two oscillations, but they act in a plane. So that's it sort of for these very, very, very strong forces. Electromagnetic and nuclear are both quite strong, and their order of magnitude is not the same, but it's of the same order of magnitude. While on the left-hand side there, we compare the gravitational parameter and the Coulomb standard parameter. So we take the same ratio, we calculate that for the we have the electric constant then and the gravitational constant, and then we have, of course, these masses. For the masses, we take, of course, the same mass as that of to calculate a Coulomb force. We're gonna take charges, electrons, the unit charge. So the mass of an electron is about 6.674 kilogram. So we take that ratio, and then we find sort of that the gravitational force is much weaker than the electromagnetic force or nuclear force. And so the order of magnitude is that factor there, 4 times 10 to the power 42, which is a rather monstrous number. So that's it. The gravitational force is really of a totally different order of magnitude. We know that, and so the distance scales are also very different. We're not talking the microwave, we're talking here the universe, planetary systems, solar systems, galaxies, and the universe itself. Just a final note on nuclear electromagnetic force. So the distance scales, the order of magnitude is about the same, but still, the fine structure constant is sort of, if there's a difference within those between the electromagnetic and nuclear distance scale, then it's the fine structure constant separates those two orders of magnitudes. The relevant distance scale for nuclear interaction, like we've in one of our papers we model sort of the motion of two opposite charges within a deuteron nucleus. So that's about 1 to 100 femtometer, 10 to the power minus 15 meter. While electron orbitals, the energy there and the force is electromagnetic, and so we know that's the size of an atom, hydrogen atom, and that's given by the formula below. So the difference between those two scales, nuclear scale and electromagnetic scale, is that factor alpha. Okay, so now we come to the universe. It's generally believed that the universe is finite, and then there's all kinds of philosophical questions on well, if it's finite, it must be in some space, an empty space, or that empty space is then infinite, or what is it? Basically, we think these questions are what Ryle referred to as category mistakes. These are questions we can't answer. We use terms that have no meaning. We live in one universe, and we can measure things, and based on that measurement, we find that the universe is finite. For the universe to be finite, so it's not a Cartesian space, with infinite with axis going to infinity. No, it must be a closed space, and that's modeled by Einstein's general relativity theory, the curvature of space, and that sort of global curvature of the universe must be positive. It means basically that if there's a center of the universe, sort of a mass of center of mass, then photons, neutrinos, anything that has energy must be traveling in elliptical orbitals. And elliptical orbitals for photons, neutrinos, of course, they travel at the speed of light, so they travel very fast. So they must also follow elliptical orbitals. It means that the photons, neutrinos that come out of high energy events inside of the universe, must at some point in time, come back. What goes around must come around. So yeah, that's interesting, and we can think about these things. The photons and neutrinos. There must be a lot of energy out there, very far away. And we will talk about dark matter in a moment. I noted that there. What's in the universe? We think ordinary matter particles are only maybe a bit less than 5%. The rest is dark matter, dark energy. So what about that actually? And we should link this to the question of the beginning of the universe. There's all kind of theories there, and many talk of the beginnings of the universe in terms of quarks and smaller symmetries that might not have been there. A lot of annihilation of matter, antimatter. But basically, the antimatter, we can't really exclude there's sort of a lot of antimatter. Antimatter gets sort of it's created quite routinely. When cosmic rays hit the atmosphere, we have creation of matter antimatter pairs. So antimatter is very much part of our universe, of our world, but because there's so much matter around, it quickly gets annihilated. We've written a paper on that where basically we say matter antimatter, these reactions, they do respect sort of the total the conservation laws. We have positive charges and negative charges, and the total number of charges gets conserved, energy gets conserved, matter gets conserved. So we can't exclude that there's sort of large antimatter concentrations in the universe. But it's not very likely actually. It's not very likely. We'll come back to that question. So we have a closed universe, and we know it expands. The observable universe, the light that comes back, that we can see comes from very far away. That light has traveled 13.8 billion light years. So that's just light years is a distance scale. So that corresponds to the age of the universe. Universe was created 13.8 billion years ago. It expands. Matter got sort of accelerated at very large velocities, and the limit of the observable universe is 13.8 billion light years away. In kilometers, that gives it out a formidable number, 10 to the power 12 times 10. You can measure it in astronomical units, the distance from the Earth to the Sun, but it only shaves, doesn't shave too many numbers away, too many zeros away. The actual size of the universe we think is much larger than that observable universe. Why? Because the universe expands. So the objects that were sending radiation out to us 13.8 billion light years ago at the edge of a universe, in the meanwhile, they've moved further. And if they would be moving at the speed of light, they would have been twice as far away now. But standard model of standard cosmological theory, these things from Wikipedia, basically, it puts it at 46 billion light years, the size of the universe, so including the non-observable universe. So that would mean that the universe expands at a very significant fraction of the speed of light. I calculated there. If the diameter is 46 billion, the radius is 23, so minus that light that comes, the distance from the objects that were sending out radiation 30.8 years ago, divided by that time is c by 3, so a third of light speed. That's quite enormous. So you might say, how do we know these things actually? How do we know that the universe expands? That's basically relativistic redshift, as we call it, the relativistic Doppler effect. Photons that are emitted by stars who are moving away from us will still travel at the speed of light. They always travel at the speed of light. That's relativity theory, special relativity theory. But their wavelength, their energy will be less, and so their wavelength will be longer. It shifts to the wavelength shifts to a lower energy spectrum. And so we're not going to go into the details of background radiation, what kind of radiation it is. But that's it basically. That's how we know why objects that are sending out light are moving away from us or towards us. We have a redshift or we have a blue shift when they are moving towards us. So that gives us a radial velocity, the velocity at which those objects travel away from us. If we think of radial velocity, of course, we should probably think of a tangential velocity. The universe might have angular momentum, it might be spinning around. Here the calculations are quite complicated because there's actually no real agreement on the question of whether or not the universe has an actual center of mass, and so these questions again are very philosophical. We can't sort of agree on a unique choice of the reference frame. If we would choose the reference frame to be that of the universe itself as an object, the whole universe, then we would think sort of all of the angular momentum of the bits and pieces inside of it should add to 0. So the total angular momentum of everything is 0. So we don't think in terms of the universe having some spin, having some angular momentum of its own. So then we turn to the what's inside of the universe. So we're not going to give these enormous numbers. There's calculations. They use critical densities, the diameter, and they calculated about 1.5 times 10 to the power 53 kg. So that makes for an enormous amount of matter particles and other particles, because the thing is sort of based on what we observe, how galaxies spin and what the mass and the energy should be there. We estimate that there's a lot of so-called dark matter and dark energy. Dark matter and dark energy, what are they? Well, it's matter and energy which we assume it's out there, but we cannot detect it, and that's why we call it dark or black. It emits no radiation. So you might think of black holes now, but thing is, black holes, even black holes emit radiation. It's the Hawking radiation. Which causes them to evaporate. And of course, the evaporation effect is there's also they also swallow matter and light, and so that keeps them growing. So there's sort of this equilibrium between, or not equilibrium, how much matter and light, how much energy they swallow, and how much energy they evaporate out. So black holes are actually, yeah, one candidate for the dark matter, dark energy, but we should be able to sort of see them because black holes do radiate. So actually, black holes are not a good explanation of sort of that dark matter and energy. We also talked about all those, photons, neutrinos. We think photons are the light particles of the electromagnetic force. They carry electromagnetic energy. They don't carry charge. Neutrinos carry nuclear energy, but it acts on the same charge, but they don't carry charge. So neutrinos are like the light particles of the nuclear force. And as said, these high energy events in the universe, the light particles got radiated out from the Big Bang, and so they're far, 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 far away. And they should come back in again. But in the meanwhile, these reactions, a lot of the energy went into radiation. So that might be another explanation of dark matter, dark energy. But the thing is, dark matter and dark energy, we think they're part of the observable universe. So it's not very likely that these light particles at the edge of our universe, account for that dark matter or the dark energy. So yeah, it's a bit of a mystery. I want to look at those calculations and see what it is. I said I don't think it's antimatter. I don't think it's black holes. I don't think it's sort of all the light particles at the edge of the universe that are there, and it must be something else. The I might add one remark. As a kid, when people told me about dark matter, dark energy, sort of the stuff you can't you can't detect because it doesn't, there's no signal. So, well, maybe there's a lot of radiation that comes from these faraway galaxies and star systems that is just simply absorbed by, galaxies and star systems that are clouds, hydrogen clouds that are closer to us. That's a valid idea, but there's two things there. First, the energy they absorb, in the long run, they must radiate it out again. Star that absorbs a lot of mass energy, will collapse into itself and then and explode again, implode and first and then explode. And so yeah, the idea that galaxies and star systems may hide or eclipse other faraway galaxies and star systems is from our line of sight is valid. But those eclipses, just like an eclipse of the moon or an eclipse of the sun, it should be temporary only. So yes, valid idea. Radiation gets absorbed, but that should be temporary only. So yeah, the question of dark matter, dark energy is probably the biggest single question that is out there. So we this gives sort of the basics of what's the universe. We have that nice illustration, took it from Wikipedia. Different scales: scale of the Earth, scale of our solar system, the closest stars, other star systems, galaxies, and then the observable universe, which, as you can see, has there's patterns there, but it all looks rather random. So my thing, we have these patterns in the observable universe. So can we sort of reconstruct um, the, um, the Big Bang? Huh? Can we sort of see where all that mass and all that energy, based on its current motion, on its current position, where it came from, and can we sort of see what that Big Bang, how it looked like? What equilibria, disequilibria were there, how hot it was, what the size was of that big blob in the beginning, big hot blob. The problem is really that it's statistical actually. The we lose track of sort of very quickly of what happened while a particle goes from here to there. This is sort of one of Einstein modeled that in 1905. He wrote these annus mirabilis papers. One of them was the special relativity theory, but in his paper on the Brownian motion, he also modeled and gave a firm mathematical basis for what we call the random walk. The random walk is a very simple idea. You take a step, step by step, and then it's random. You toss a coin perhaps, or maybe Schrödinger's cat. The cat is still alive or the cat is dead. You open the box, you look. And based on whether or not the cat is alive or dead, you take a step back or you take a step away from where you started. And so there's three trajectories there. You can see it's really random. We sort of move away and back towards the place where we came from, but in the end, we don't move very far away from where we started. And the real thing there is, at the bottom half of that graph, you have two different trajectories, two possibilities to get that, after 30 steps, at that distance, what is it, minus 8 steps away from the center in the negative direction. But we can't really, with that information that we are now where we are, trace back where, what the trajectory was. And that's something very particular. The uncertainty I introduced here is rather rough. It's either we go here or else we go there. Two opposite directions. But in general, the analysis is valid. If there's some kind of irregularity, some kind of a randomness, that gets magnified very, very quickly. The information gets lost. I'll read it out there. So the tiniest irregularities really are magnified, and we get complete randomness. And you might say, well, it's because of accuracy and whatever, lack of accuracy. But no, actually, whatever accuracy, no matter how precise, our predictions will not be varied for a very long time, and that length of time is not very large. It's not like time is millions of years if the accuracy is 1 part in a billion. It goes logarithmically with the error, and in a very, very, very tiny time, we actually lose all information. So no, the answer is we can't really reconstruct the past from the present. So yes, the Big Bang, yeah, it was there, but was there one Big Bang, or were there maybe several Big Bangs at different distances in space and in time? We do not know. It does help to sort of, and it's probably logical to try to think about, contracting universe. So the current universe, we might have had hydrogen, proton and electrons. Said forget about quarks and whatever. We have electrons and protons, positive and negative charges in equal amounts still today and at the beginning. So you might think of that philosophically, the male, the female, the one element and its opposite and whatever, but it sort of doesn't help very much. That's sort of an intro, very human idea, but yeah, it doesn't qualify for logic. So, but yeah, we had hydrogen. We still have hydrogen. Most of it is hydrogen, the matter in the universe. We also have a lot more massive elements now. So contracting universe, when the universe is going to go into contraction again, it's going to contract into local clusters of mass and energy. But yeah, we'll have more massive elements in those clouds that then form stars, and so we'll have different reactions, fusion reactions still, but also fission reactions. And so the whole idea is, the coming into being of the universe and how it's going to contract back is probably not a linear process. So that's why we should not exclude there were like several big bangs at different places in time. And the basic thing, though, is that, and that's something good to know, is that the universe expansion as well as its collapse is governed by the same laws. You have all these theories out there that constants of nature might have changed, and said these symmetry breaking and all the kind of things. But you can forget about that. The laws are and have been the same, so that brings sort of an eternal logical element to the chaos, let's say. All right, I'm gonna move to the last and most interesting topic: life, life on Earth, life somewhere else, perhaps. I put some summaries there, but it's really, I mean, it's remarkable how life evolved. You know, you have atoms forming like more stable is, you know, less energetic combinations by sharing or exchanging valence electrons, and then these molecules arranged into organisms. Organisms are very vulnerable to high energy radiation. You know, the incoming particles will destroy them. But yeah, organisms developed on planets because, you know, it's cool here. There's an atmospheric layer that protects those organisms from that high energy radiation, and organisms turn out to be you know, very they adapt to changing circumstances. So um, they are maybe vulnerable, but they reproduce really well and they adapt to changing circumstances, changes in the atmosphere. So that's sort of, you know, it's quite a long way, because, you know, from an organism, from a bacteria or a virus, you know, to see crawling insects and crabs and spiders and conscious, I mean, us, Homo sapiens, how we came into being, you know, it's weird, but it's explainable. Just to note on that, insects, you know, they haven't changed all that much, so they're probably more robust to changing circumstances, so they don't need to change. While man adapted himself, and but man adapted also its environment, and that's quite unique. Or, you know, he searched for other environments, but also sort of part of that search for better chances of survival and, yeah, successful replication. So we do obey the laws of the universe. Sometimes people think, you know, life is, you know, not according to whatever law, but we do. Energy dissipates. We know that entropy increases. We do burn a lot of energy to, you know, get our cars rolling, or, you know, produce mobile phones. There's a lot of waste. You know, we gather a lot of data, information, but you know, it's quite powerful. If the data and the information is not immediately useful, we store it in our head or on paper, or we share it for future purposes. Or else, you know, we have that logic that discards data information as useless, so we won't use it anymore. We'll look for other ways. Um, so that's the miracle of life, and it's but yeah, it does feel kind of lonely here sometimes, right? So you wonder, is there life on Venus or on Mars? We know that recently, you know, there were traces of biogases discovered in the atmosphere. Biogases, yeah, well, they're produced by bacteria or virus, and that's where you know, I put that probably the biggest danger of these other life forms is well, the COVID crisis showed we're not very good at dealing with sort of, you know, small microorganisms. They usually harm us. We're not prepared for them, and so it takes a while before we build up our immune system for it. So other life forms, you know, nearby, if they exist on Mars or Venus, the biggest threat is probably, you know, they'll harm us, and probably, you know, their intelligence is very basic. It's about survival and reproduction, not about, you know, what we're talking about here, concepts and theories. And so, is there a life? Well, what's life, and is it useful for us? So most probably not. Other life forms, you know, they're probably going to harm us. Even intelligent beings outside, you know, they'll look for new territory, and they'll probably see us, and we'll see them as an invasion. And so we're likely to, you know, to start a war very quickly. And well, if they come that far with starships, then we're probably going to lose that war very, very quickly. The other thing is really communication. Communication is going to be difficult, you know, with other intelligent beings. Not so much because we can't figure out the language or whatever, but it's just the near distance. The nearest star system out there is the Alpha Centauri system, and that's about 4.3 light years away. So if we're sending signals out and we're doing that sort of, you know, hey, we're here, you know, please respond. Well, it takes 4.3 years, you know, to get to the closest system where there might be life, and then, so yeah, perhaps they are sending signals out to us, but then, you know, the mere distance also makes that the intensity of those signals is going to be very, 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 very weak. So too weak to detect because energy radiates out. It's the law of Gauss. Yeah, that signal is just going to get lost in space. Just to sort of put things into perspective, mankind has been on this program for quite a while, actually since the 60s, to send out probes in space, probes that leave our solar system. And so one of the most successful ones was Voyager 1 and 2. NASA's Voyager 2 has left the solar system, and it's 18.7 billion kilometer away. So in light years, that's 0.002. So it's really a fraction, a very tiny fraction of that distance towards the nearest star system. So what's going to be the use of the Voyager space probe now? Well, we don't know. It yielded very valuable data on our planetary system. It passed Jupiter, Saturn, Uranus, Neptune in 1979, 81, 86, and 89. But then now it's gone, it's out, and we communicate with it. Voyager 2, we didn't communicate with it for almost a year because the radio station in Australia that communicates with Voyager 2 was down for maintenance, but it still works. It's an old vehicle, 44 years old. But yeah, we're not gonna hear from it. We will hear from it, but we won't see much. It won't measure much. It won't see much. It's so the Voyager 1 is another one, Voyager 1 and 2. That's gonna reach this another star system, Sirius system, and but it's gonna take 40,000 years from now. And a Voyager 2 is headed for another star. It's about the same thing. 40,000 years from now, it will be there. But we'll have lost contact with these probes. They will not be functional. And also, I said, we won't be alive. And then, to communicate a signal back, relay information, that they might, then transmit to these other intelligent beings that we may or may not discover there, is just hopeless. The distances are just too large. The spacecraft going in other directions. I mentioned NASA's New Horizons probe there, was launched in 2006. So that also sort of gave us a lot of information on, might there be life? Explore the Kuiper belt. The dwarf planets Pluto, Charon. Charon is a moon of Pluto, but about half of the size, so it's a dwarf planet. Yes, valuable information, but nothing that sort of confirms, that we are not alone in our planetary system. On the contrary, we think we are alone as intelligent beings on this planet Earth, and so we had better take care of it as we can for future generations. I'm not a pessimistic. I think climate change is real. Sea levels might rise, might not rise. There's a thing there that I want to note, though. The rising sea levels. Antarctica is like a big iceberg. But ice, the volume of ice is larger than the volume of the water it contains. So if that's going to melt, that's not going to add any more volumes to the oceans. The melting of Antarctica is not going to cause a rise in sea levels. The masses of ice, the glaciers on the North Pole and Greenland, yes, that's sort of ice that's going to go into the ocean. But the ocean is going to evaporate. The Sahara is going to get greener. Probably it's going to cause, of course, all kinds of disturbances in the weather system. More hurricanes, more this, more that. But climate change. It says climate change is real, but what the effects are going to be, how we're going to adapt to them. I'm actually quite optimistic on these things. But that's a bit of a different discussion. And so I will end my presentation here. We have, it was 40 minutes, 10 minutes per slide, which is a little bit much. But I hope you enjoyed it. I wish you a very happy Valentine's Day. Take care of yourself. Take care of of the people you love. Take care of your family. And that's it. Have a nice day.